Well, we're on chapter 4 now, going on building up to chapter 3. So in chapter 3 we learned all about stoichiometry, and the question start with the question is, does your car run on air or fuel? Well, this is where you're at so far in the course. We have octane. Gasoline's a mixture of things, but it's predominantly octane. And oxygen. Burns oxygen to form carbon dioxide and water. So you know that the molecular weight of octane you can figure out to be 144 grams per mole, and oxygen is 32 grams per mole. So two octanes is 228 grams, 25 oxygen is 800 grams. That's 1,028 grams on the left side of the equation. On the right side of the equation, there's 16 carbon dioxide and 18 water. And the total mass of that is 1,028 grams. So 1,028 grams in, 1,028 grams out. So you think, oh, my car runs on gas. Not really. It runs more on air. So on a factor of almost 4 to 1, right? So you have 228 grams of fuel consuming 800 grams of oxygen. So really your car more runs on air. Of course, you don't really worry about your car running out of air. You worry about your car running out of gas. Why? Because there's just so much air. So that's one of the things we're going up to is a limiting reagent. So at a huge amount of excess, the limiting reagent is one that's not in excess, like fuel versus oxygen in the air. Now, for somewhere else, like if you're in space and you're using a chemical reaction to generate thrust, you'll need to bring the oxidizer with you. Don't really have to worry about that on the ground. Another thing to note is that 200 grams or 220 grams of fuel makes about 700 grams of carbon dioxide. Now we were talking about perhaps taxing carbon dioxide via carbon credits. It was proposed $30 a ton, and that can drastically increase fuel prices. So that's one thing. The legislation never passed, or at least hasn't passed as I've spoken in this video. But that's one of the thoughts there. So you have coal or you have fuel, and generates carbon dioxide, and the carbon dioxide, because it's absorbing 32 grams of oxygen, it weighs a lot. And we're studying these reactions more and more about carbon sequestration. So we'll have an example later. We'll talk about that. Okay, but let's move on. And maybe you think back to your youth and how to make a Happy Meal. What's in a Happy Meal? Well, you've got a toy. You got a burger. Some sort of fries. I know it can be apple slices or something like that. And a drink. All 1 to 1 to 1 to 1. So if you have 1,000 toys, 1,000 burgers, 10 fries, and 1,000 drinks, how many Happy Meals can you make? You can only make 10. Why? Because you're limited by the number of fries. If you call your manager, he says, well, all right, we'll get 10,000 toys to go make me more Happy Meals. Say, nope, sorry, I can only make 10 because I'm limited by the fries. So there is something that limits the chemical reaction. So now this is all a 1-to-1 ratio. What about the ham sandwich reaction, where you have 2 pieces of bread and 1 piece of ham to make a ham sandwich? Well, what would happen if you have 100 pieces of bread and 100 pieces of ham? How many ham sandwiches can you make? You can only make 50 ham sandwiches, and then you would also have 50 slices of ham left over. Why is that? Because there is a 2-to-1 ratio between the bread and the ham. So you need twice as much bread. If you want to make 100 sandwiches, you need 200 pieces of bread because of that 2-to-1 ratio. So that's another thing that would be important in balancing chemical reactions and in limiting reagents, is to look at the stoichiometric ratio. Okay, so let's move on. And I told you about carbon credits. There are lots of uh, studies going on about plants, looking at different things: corn, miscanthus giganteus, trees to sequester carbon dioxide. So, in case carbon credits are a reality, then people can generate carbon credits by sequestering carbon dioxide. So, there's been quite a bit of research in this. And algae here is one. You have a particular plant, probably this would probably be algae, consumes 37.8 grams of carbon dioxide in 1 week. Assuming there is enough water present to react with all the CO2, how much glucose in grams can the plant synthesize from the carbon dioxide? Okay, so how do we do this problem? Do dimensional analysis. So start off with 37.8 grams CO2. So hopefully you're at the point where you're like, grams, I want moles. So mole CO2, and that's 44 grams per mole. Oh wait, so if it's 44 grams per mole CO2, and I'll put CO2. And then the next step here is that for mole GLU is glucose, you need 6 moles CO2. So this here is the new step. So where do I get this from? I get this from this ratio here. The fact that there's, for 6 parts CO2 forms 1 part glucose. And then it's what's grams, 1 mass glucose in grams, 180 grams glucose per mole glucose. And we did that calculation in a previous chapter. So, and this one though, I know that the CO2 is the limiting reagent because it says excess water. That's the other hint with this. So I'm not going to pause this. I can put this in 37.8 divided by 44 divided by 6 times 180, and we get 25.7 grams of glucose. GLU is glucose. Okay. So let's look at some pictures with limiting reagents. So the flask contains a mixture by the image on the right. So after reactions have reacted, what is limiting reagent? So, and this is a reaction. This is ammonia synthesis reaction. So nitrogen plus 3 hydrogens makes 2 ammonias. So we need to have it's a 1:3 ratio. So just looking at this, the number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, and there's 2 nitrogens. So for those 2 nitrogens, limiting reagent with the 2 nitrogens, it would need 6. So we're going to react 6 of those hydrogens, and we're going to have 2 hydrogens left over, and we're going to form 4 ammonias, right? So if 2 nitrogens react, we're going to have 4 ammonias. So we find which one is that, and here we go. That the answer then is this part C. If you look at the other ones, yeah, there's 4 ammonias, but there's also excess hydrogen. And this one here, this one just didn't react all the way. So needs to be that. This one is correct, but it's not yet completed. Okay. So let's look at a problem. We don't know what the limiting reagent is. So ammonia, for instance, can be synthesized by this reaction. That's not how we make ammonia. We make ammonia over an iron catalyst and make it from nitrogen and hydrogen over iron. But you could do this. It's done very rapidly. This one would not be a very practical reaction. But let's go ahead and look at it. So this one, we have to do both. We have to figure out which one gives us the lower amount. So when you do theoretical yield, it has to be the lower amount. So, honey, the gas is still on. I can smell it. Oh, it's not? Okay. Okay, so do both and figure out what the lowest one is. So let's look at nitrogen monoxide. 86.3 grams nitrogen monoxide. And so we're going to convert that to moles. Moles, and nitrogen is 14, oxygen is 16. That's 30 grams nitrogen monoxide. And then we have 2 moles ammonia to 2 moles nitrogen monoxide. I would just say 1 to 1 and get rid of it that way. But if you want to keep 2 to 2 there, that's fine. And then 17 grams ammonia to mole ammonia. And then we do the other one. 25.6 grams hydrogen, mole hydrogen, 2 grams hydrogen, and then we have 2 moles ammonia to 5 moles hydrogen, and then 17 grams ammonia to mole ammonia. And so we just do both and see which one is smaller, and I will do that for you. Okay, so if you look at this, we have 48.9 grams ammonia from nitrogen monoxide and 87 grams ammonia from hydrogen. In this case, you have to go for the lowest one, and I will write the unit there. And that's the answer. 48.9, go for the lowest one. So, next one here, do this on your own. Try it out. Pause the video and try it out. And the answer is B. Okay, limiting reagent and theoretical yield. So, we obtain titanium metal by this reaction here, titanium dioxide, also known as rutile. It's titanium ore. We react with carbon to form titanium metal and carbon monoxide. It's usually liquid titanium, but that's fine. This is called reduction of carbon, and it's how we get the vast majority of our metals. Pretty much we make all metals this way with the exception of gold and aluminum, maybe platinum. It's because we just take ore, we crack it by heating it up in the presence of carbon and in a blast furnace, and we get the metal. That's and there's other tricks too. You can add lime. Lime helps pull out the impurities, but that's more or less how this is how it works. So now we have 28.6 kilograms of carbon react with 88.2 kilograms of titanium dioxide, and we produce 42.8 kilograms of titanium. What is the limiting reagent, the theoretical yield, and the percent yield? Okay, so the percent yield, this is the formula, is the actual yield over the theoretical yield times 100%. And so first things first, let's figure out the limiting reagents and the theoretical yield. So we have 28.6 kilogram carbon, 1,000 grams carbon per kilogram carbon, mole carbon to 12 grams carbon, and we have mole titanium to 2 moles carbon. And what is the molecular weight of titanium? I have to look to my periodic table to figure that out. It's loading. Titanium is 47.9. So 47.9 grams titanium per mole titanium, and then kilogram titanium, 1,000 grams. Okay. Do the same thing for titanium dioxide. We have 88.2 kilogram titanium dioxide, 1,000 grams per kilogram. I know titanium dioxide, mole TiO2. So what is the molecular weight? So it's titanium. So it's 47.9 plus 32. So that's 32, so 16 times 2, so that is 79.9 grams TiO2. And then mole Ti to mole TiO2. And then we have 47.9 grams titanium per mole titanium, and then kilogram to 1,000 grams. So I put the 1,000 grams in there, and if you haven't noticed, they cancel. These two lines cancel. But you multiply by 1,000, divide by 1,000. There's a shortcut. You can do something called a kilogram mole. Everything you see in the periodic table is called a gram mole. It's normal. It's 6.02 times 10 to the 23rd grams per mole. A kilogram mole is 6.02 times 10 to the 20. Well, it would, for grams, it would be then 26. That's the just 3 in the exponent. There's also a pound mole. A pound mole is the amount for having, like, carbon's 12. It's 12, whatever the 12 pounds of carbon is a pound mole of carbon. So whatever number that is. But it's used. It can be used commonly in industry. It's because, at least here in the United States, it's because we're weird. They don't do it anywhere else in the world. They use kilogram moles in other places in the world, but not pound moles. Okay, so let me put this in the calculator for you. Okay, I'm almost done. Okay, I'm back. I've done the calculation. And looking at the carbon, 57 kilograms is what we produced. And then the looking at the titanium dioxide, 52.9 would be produced. So limiting reagent is the titanium dioxide. And now let's look at the theoretical yield. So the actual yield was 42.8 divided by 52.9. So I'll just go ahead and put that in my calculator. The calculation's up there for you. This one's pretty simple. So that is 80.9%. So the other question is, why are we not getting 100%? Why is there only 80%? Well, you dig ore up from the ground. Okay, it's not a pure substance. We're not looking at pure titanium dioxide when you mine it. It's got other stuff in it. It's got dirt in it. It's got various impurities in it. The other thing is, if you look at this, if I were the plant manager and this is the chemical engineer running this problem, I would go and I would give them the big pat on the back and hopefully a raise, because this chemical engineer knows what he or she is doing. So why is that? So carbon is cheap. Ore is expensive. So what did this person do? The person had the experiment such that the expensive stuff was the limiting reagent, not the cheap stuff, but it's just barely the limiting reagent, and it's enough excess that it'll do. We're not going to waste it. I mean, we have a little excess carbon, but because like carbon's cheap, it's not super in excess. It's pretty close. So this engineer knows what he or she is doing. The other thing, though, if you look at the amount, 57 kilograms, or well, 52.9, excuse me, that's the limiting reagent. We're looking at 50 kilograms ish, 50 kilograms. That's nothing. So when you make metals in industry, you're talking about thousands of tons, millions of tons. This is more likely what's called a pilot plant. So what is a pilot plant? It's somewhere in between the benchtop chemistry and the mass production chemistry. So think about making cookies, for instance. So when you make cookies at home, if you make them from scratch, you go and you grab the flour, the sugar, the butter, that kind of thing. You mix it up in your kitchen in a bowl, then you throw it in your oven, you wait, and the cookies come out. So that's kind of like how we do chemistry in a laboratory. Then, is that the way that the big cookie companies make cookies? No. They have an automated process that covers many different machines. It's very automated, made in huge quantities. But when you do this, you have to learn how to make it. So especially if you have a change. So let's say you're switching from chocolate chip cookies to Christmas cookies. So your line changes, and what do? You have a smaller line. That's called a pilot plant. That's just a smaller automated process. And if you make a mistake, if you keep the cookies in the oven too long and you burn them, that's unfortunate, but you're only burning 50, 100 cookies in a pilot plant rather than 10,000 cookies in the scale up. So Of course, after the pilot plant, then I use the word scale up. Then it's scaled up to the massive production. There's always a little bit of tweaking here and there, but the important thing is to do all your lessons, learn all the problems, all the tolerances in the pilot plant in the small amount before you go to the huge production line. And that's more likely what this is. This looks like a pilot plant that they were trying to figure out how much carbon, if you can actually get a little bit more of titanium from the titanium dioxide, and how much more. Then it becomes a cost analysis. So let's say that you get a little bit more titanium, but the carbon's more expensive. Maybe it's better not to spend the extra money on carbon and have a little bit, not get as much out. So that's where problems like this go. And that's what we do with chemistry and this kind of knowledge in the real world. Okay, last one here. 50 grams oxygen and 850 grams hydrogen make 50 grams of water. What's the percent yield? So obviously the oxygen is the limiting reagent, and if you recall from the earlier one, we have 112.5, so half of that is 56.25, so 50 over 56.25, and that's going to be probably 90%. Let me check with my calculator. So 50 divided by 56.25. And that's, yeah, 88.9%, which is close to 90%. So, okay, done with this video. I'll see you for the next one.